5.4 is the normal distribution. Normal distribution, our first blank here, is data that when graphed as a histogram or frequency polygon results in a unimodal symmetric distribution about the mean. So it's going to look like a curve, a bell, or parabola, whichever makes most sense when you try to picture that. The normal curve is a symmetrical curve that represents the normal distribution. It's also called a bell curve. I'm going to draw a few examples that I encourage you to write down as well for a histogram or a frequency polygon that's going to resemble the shape of a bell curve. So for a histogram, if we have our bar graph, that means that our graph is going to increase almost equally on both sides, where it'll reach its highest point, possibly duplicate, and then look very, very similar on the way down in terms of the left-hand side. So we can see if we compare the shape, this is in the shape of a bell curve. If I go to a frequency polygon, that graph would look, or that's the one where we connect our dots. So if I have data entered, it's going to also take the shape. When I connect, it'll look like a bell curve as well. Okay, so we know that a graph is normally distributed if it takes on the shape of a curve, bell, or parabola. Properties of normal distribution graph means that it has a mean, that symbol that we saw when we were using standard deviation here, and a standard deviation, which is here. So we have the mean, which is going to be the middle of our graph, and we're going to have standard deviations on both sides. A normal distribution graph is symmetrical about the mean. So about the middle, if I drew a line in the middle, it's going to look the same on both sides. It's symmetrical. Almost all the population lies within 3 standard deviations of the mean, and that will make more sense once we draw a diagram of what that looks like, what the standard deviations look like in a normal distribution graph. The horizontal axis is an asymptote, and that's a new word for you guys. So what an asymptote means is that it never touches the horizontal axis. There's like an imaginary line that won't ever let us cross it. So asymptote means it'll never touch the horizontal axis. The total area under the curve is 1, and it follows the 68, 95, 99.7 rule. What that means is we're going to break that down. So 68% of the data lies within 2 standard deviations of the mean. So let's write that down. 68% of data is within 2 standard deviations of the mean. 95 means that 95% is within 4 standard deviations of the mean, so including the first 2, and we're adding another one on each side. So 95% of the data is within 4 standard deviations of the mean. And the 99.7 rule, you can probably guess now, 99.7% of the data is within 6 standard deviations of the mean. What that's going to look like in a diagram is the following. So draw this with me. We'll leave that up so that we can see that data, but we'll draw right underneath. So drawing a fairly large bell curve, if you can, we're going to split it up into sections. So right down the middle, this is where our mean is going to be. And if you want to label that, that is our mean. What we said over here on the left was that there's 68% of data within 2 standard deviations of the mean. So we want to make some rectangles here so that we have two different sections on one on each side of the mean. So if this whole total, it needs to be 68%, then this half will be 34%, and this half will be 34%. That satisfies our 68% of data between two standard deviations of the mean. The next one says there's 95% of data within 4 standard deviations. So adding another rectangle, I have 4 standard deviations, and I have 4 sections about the mean. And from this end to this end needs to be 95. So if we have 34, 34, we have 68. That means we need to have 13.5 here and 13.5% here. 13.5 plus 34 plus 34 plus 13.5 gives us our total of 95%. Next, we just have two little ones off to the side, each of 2.35%. As our totals for 6 standard deviations in our notes above, it says that that needs to be 99.7% of the data, leaving our very, very small corners being 0.15% because there's 0.3% left that's not included in our 99.7%. So that 3% is distributed, each half is 0.15 on each side of that graph. So that's what our normal distribution graph looks like. This is what you want to know. You're going to want to know that spacing. You're going to want to understand that your mean is again in the middle, and that you have a standard deviation, a negative standard deviation, a positive standard deviation. Then you have a positive 2 standard deviation and a positive 3 standard deviation, a negative 2 standard deviation, and a negative 3. That's how you would label that. So when I talk about data, say here, this is 1 standard deviation away from the mean. This is minus 2 standard deviations away from the mean. And we'll get to more of that when we do an example. So example 1. A company has determined that the lifetime of the car battery it manufactures is normally distributed with a mean of 48 months and a standard deviation of 8 months. So breaking down this question, when it says that it's normally distributed right here, we know the shape it's going to take. It needs to take that bell curve or that parabola shape. We have a mean of 48, so the middle of our graph is going to be 48. So if you want to write that, that's going to be our middle. And then we have a standard deviation of 8 months. Each section is going to be 8 months. Each section, or you can say each standard deviation away, is going to be a span of 8 months. The first step we want to do is sketch that. So let's draw our bell curve. We know the middle is going to be 48. 1 standard deviation to the side, we're going up 8 months. So this will be 56 months. This will be 64 months. This will be 72 months. And to the left, since we're going before that, we need to subtract 8. This will be 40 months, 32 months, and 24 months. Now we can also fill in the percentages that we talked about on the previous page. So we know that the first 2 standard deviations away from the mean is a total of 68%, so we can write in 34% here, 34% here. If you're not sure, you can look back at the first page too as to the percentages that you put inside of each standard deviation. The next one is 13.5 on both sides, 2.35%, 2.35, and then 0.15%. 0.15. It's a little bit hard to read with my marker, so if you're not sure what I wrote down, just rewind there and re-listen to what I said. So outside in, 0.5%, 0.5 on both sides. As you work in, 2.35% on each side, 13.5% on each side, and 34% on each side. Part B says, what percent have lifespans less than or equal to 64 months? So that's where we want to. I'm just going to quickly draw another one. And we can see where 64 is here in the top. So I know that if I have my mean, my average, there's one standard deviation, which is 56, and the next standard deviation, this is 64. And it's asking less than or equal to 64. So that means from here on and to the left. So I'm going to highlight what it's talking about here, from 64 and less. So that's the rest, this whole part of my graph that's to the left-hand side of 64. So it's asking what percentage is that, and if we have all of our standard deviations written in there, we know how much, based on the percentages in A, the total coverage in that from less than 64. So let's add that up. Right here, we'll have 0.15% plus 2.35% plus 13.5% plus 34% plus 34% plus 13.5%. And we stop here because on the right-hand side of 64 would be your other 2.35% and your 0.15%. So this total is the percentage less than or equal to 64 months. When I add that all up together, I get 97.5%. A little bit of a quicker way is, you know this half here is going to be 50%, right? This is all of this, everything on the left-hand side will be half of your data. So you can start there, 50% plus, we know this first standard deviation is 34%, plus this extra one is 13.5%. Again, would still give you the same number. So if you want to do it in less steps and you understand that 1/2 of this normal distribution graph, this curve is 50%, that's fine as well. Part C. What percentage have lifespans between 40 and 72 months? So now we need to look at our graph when we're looking for the percent between 40 and 72. So if I look at my main graph, that's now here between 40 and 72. So between 40 and 72, what percent? So we want to add up all the percentages in between that area. So again, if you want to draw another diagram just satisfying that situation mentioned, we have our average. We know that 40 is one standard deviation to the left, and 72 is going to be the third standard deviation, 1, 2, 3, 56, 64. So here's 40, here's 72. We're looking for the space in between those standard deviations. What percentage has a lifespan in between 40 and 72 months? So again, we just want to add up those percentages. We know that if this is the mean, one standard deviation on both sides is 68%, plus we've got that 13.5%, plus our 2.35%. That totals to 83.85%. So 83.85% of these batteries have a life expectancy in between 40 and 72 months. Part D, between which lifespans did 95% of the batteries lie? So if we want to think back to the first slide, I'll hop back over here, and we talked about our 68, 95, 97, or sorry, 99.7 rule. 95% of the data right here is within 4 standard deviations of the mean. So we'll go back here and we will draw what that looks like. We have our bell curve graph. Here's our mean. 1, 2 standard deviations, 3, 4. So mean is here. We have 1 standard deviation, 2 standard deviations, -1, -2. That's 4 altogether. So what were the months at the bottom of our second standard deviation to the left and our second standard deviation to the right? So let's compare with our graph at the top. So our second standard deviation to the left is 32, and our second standard deviation to the right was 64. So what we would write for our answer here, which lifespans have 90%? Between 32 to 64 months was 95% of the batteries, within 2 standard deviations on both sides of the mean.